So we are familiar with bonding in carbon monoxide and nitrosyl, and the only difference between carbonyl and nitrosyl is the addition of one electron and one proton. And when we add one electron and a proton to carbonyl, so it becomes equivalent to nitrosyl. Or if we, for example, this strategy is very useful in explaining bonding in nitrosyl. If we take on-board bonding in carbon monoxide, take molecular orbital diagram which we have already drawn for carbonyl ligand and put one electron in that diagram, and you will be able to place the electrons, and also you will be able to explain the orbitals, that which pair is available for bonding in order to make a coordinate covalent bond with metal center, and if the ligand is capable to accept electron from the metal center, so where the ligand will put those electrons. So, and these are the strategies to explain the coordination chemistry of such type of ligands. So for sure you are now familiar with coordination chemistry of carbonyl, and inshallah it is very easy to explain the coordination chemistry of nitrosyl based on coordination chemistry of carbonyl. So there is a difference of a proton and of an electron. So put one proton and one electron on carbon atom, and definitely the electrons are orbital subshells of carbon. They were presented on left hand side of the molecular orbital diagram. So we have to explain the bonding in nitrosyl while applying valence bond theory approach as well as molecular orbital theory approach as we have applied to carbon monoxide, and then we will come to know that what type of pair of electron is available and where the electrons available for bonding with metal center is are situated or polarized on oxygen, or they are polarized on nitrogen. So now uh, we have quite enough knowledge to know or to determine the coordinating site or ligating site of a ligand, that which site will be oriented toward metal center for coordinate covalent bond. So either oxygen or nitrogen, but this we have to explain logically with technical reasonings. Now to give this nitrosyl cation, add an electron to pi star orbitals uh, to account for the extra valence electrons on nitrogen versus carbon. So this is actually the nitrosyl cation, and while we are explaining the bonding in nitrosyl cation, we have to remove an electron. And if we are dealing with a species with one electron more than carbonyl, so that species, for that species, what we have to do, so we have to put an electron in pi star orbital of the carbonyl uh, diagram, but already we have replaced a carbon by nitrogen, and this we are coming to explain in coming slides. Now, this is a complex, molybdenum complex with cyclopentadiene and carbonyl ligands and linear nitrosyl fragment. So this fragment actually makes a bond with metal, and metal NO fragment is linear. So remove the unpaired electron from nitrosyl, because nitrosyl possess two types of electron. One is pair and the other one is unpaired, as we will explain it later on. When we remove this unpaired electron, then the nitrosyl becomes two electron ligand, and nitrosyl, by removing that electron, it adopts positive charge, and as a result of this positive charge, where we have to move that electron, so that electron can be placed on molybdenum atom. So molybdenum will get anion, or it will get negative charge, and nitrosyl will get positive charge. Now this molybdenum negative and nitrosyl positive, they reacts with each other, and this already we have done, that we have placed electron from nitrosyl on metal center. Now nitrosyl, when it is positively charged, so it is two electron donor. And when it is two electron donor, so look at this complex. and count all electrons around the metal center, particularly valence electrons around the metal center. So this complex is 16 valence electron complex, and 16 valence electron complex means number of electrons contributed by cyclopentadiene, number of electron contributed by two carbonyl fragments, and number of electron contributed by a nitrosyl. So this is a complex which possesses one Cp, two carbonyls. So one Cp and two carbonyls, this is starting precursor or starting material, and this starting material is treated with nitrosyl cation. So nitrosyl cation, which actually makes a linear fragment, and this linear fragment is also two electron donor. So when we add two electrons to 16 valence electron fragment, so it becomes 18 valence electron complex, and this 18 valence electron complex is now stable. So how bonding in nitrosyl is, this we have to explain on the basis of molecular orbital theory in next slide. So this is molecular orbital diagram of nitrosyl. We have to place the atom which is comparable, which possesses comparatively less electronegativity on left hand side, and the one with high electronegativity on right hand side. The number of electron in s orbital of oxygen, they are 2, and in p orbital they are 4. Similarly, in s subshell of nitrogen there are 2 electrons, and p subshell of nitrogen is half filled with 3 electrons. So placing these electrons in bonding molecular orbitals, so one pair has to be placed here, and this is bonding molecular orbital. The counter orbital is anti-bonding molecular orbital, and the other pair will occupy the anti-bonding molecular orbital. So this is the s orbit, which contributes nothing toward bond order, and bond order in this case is 0. Now in case of p, there are 4 electrons with oxygen and 3 electrons with nitrogen, so total number of electrons are 7. We have to place 6 electrons in these 3 bonding molecular orbitals. Among them, one is sigma bond and two are pi bonds, and the one electron which is remaining, definitely the one orbital which is available for that electron is pi star orbital. So this is the electron which is actually unpaired, and whenever a species possesses unpaired electron, so that species is called free radical, not a compound. So nitrosyl is a free stable radical, it is not a compound on the basis of this unpaired electron. Now coming toward HOMO and LOMO orbitals, so put energy axis here, and energy increases upward. So these are the orbitals which are completely filled, or which are filled orbital, and whenever we arrange these orbitals in order of their increasing or decreasing energy, so energy increases in this direction. So this orbital is with lowest energy, and this orbital has the highest energy. So the one which possesses highest energy, that is called HOMO, or highest occupied molecular orbital. Now these orbitals are unoccupied orbitals, and on the basis of energy, these orbitals have also been placed in order of their increasing or decreasing energy. So these orbitals possess lower energy, and this one possesses higher energy, and orbitals with lowest energy which are unoccupied, they are called LOMO. So these are LOMO. Now coming toward polarization of these LOMO and HOMO orbitals, so the species are the what we can say, the atom which is involved in bonding and possess high electronegativity, we place it or we represent it on right hand side, and its counter atom with low electronegativity on left hand side. So also accordingly we have to polarize our molecular orbitals also polarize on these atoms. And molecular orbitals are polarized on high electronegative species, or they are more closer toward high electronegative species, and anti-bonding molecular orbitals are closer, or they are polarized to the species which possess less electronegativity. So anti-bonding molecular orbitals are polarized at nitrogen, and bonding molecular orbitals are polarized at oxygen. So this is now anti-bonding molecular orbital, and the pair which we call, or this orbit we call as HOMO, or highest occupied molecular orbital. So this pair of electron is available for bonding with metal center. This pair will be donated toward metal center in order to establish a coordinate covalent bond. And this pair, if we look, so this is polarized on nitrogen, not on oxygen. Therefore, nitrosyl will get attached to metal center through nitrogen, not through this center. Similarly, whenever the ligand is capable to accept one electron or more than one electron back from a metal center, provided that metal possesses such number of electrons, then these orbitals are available for acceptance of those electrons from metal center. And if you look at these electrons, these orbitals, that where they are localized or polarized, so these orbitals actually belong to a nitrogen, not to oxygen, because they are bonding orbitals, and bonding orbitals are polarized on oxygen because they possess more characters of oxygen. Electrons will be accommodated preferably from oxygen, not from nitrogen. And these orbitals, they are localized on nitrogen, not on oxygen. So if this ligand is pi acceptor, because and for sure this ligand will be pi acceptor because it possesses pi star orbitals. So on the basis of these pi star orbitals, the ligand is electron donor through nitrogen and it is acceptor through nitrogen. Therefore, this ligand will act as soft ligand, and in other words, we call it pi acceptor ligand. So this is molecular orbital treatment of nitrocell.